I am going to deliver a lecture on chemical bonding. Today we are going to discuss about the molecular orbital theory. What is molecular orbital theory? This theory is proposed by F. Hun and R. S. Millikan in 1930. The main points of molecular orbital theory are: atomic orbitals can mix together to give a new set of molecular orbitals and belongs to the entire molecule. The electrons belonging to two bonding atoms are controlled by the complete molecule. One molecular orbital is formed for each atomic orbital used. In an atom, atomic orbitals determined by various values of quantum numbers, while in this case also the molecular orbital determined by various quantum numbers. This molecular orbital theory, it also follows Pauli's exclusion principle of 2 electrons per orbital occupy specific region of space. The molecular orbital can also accommodate only a maximum of 2 electrons. This is similar with the atomic theory of molecules. The Hun rule of maximum multiplicity also followed in case of molecular orbitals. So there are certain similarities between the MOT and VBT, that is in molecular orbital theory and valence bond theory. Orbitals are known as the wave functions in modern quantum mechanics. Wave function psi contain mathematical terms that can have positive and negative values. Their positive and negative values determine the bonding and anti-bonding conditions. An s orbital value can either be less than 0 or greater than 0. The two lobes of p orbitals are separated by a node and have opposite sign. Their same sign overlapping will favor bonding and opposite sign favors anti-bonding. The atomic orbitals combine according to linear combinations of atomic orbitals. In this case, the electrons can be thought of as moving in a molecular orbital whose total volume is approximately to the sum of the volume of atomic orbitals. So in whole of this molecular theory, the orbitals can be treated as wave functions. These wave functions are of opposite sign. The s orbital can have two opposite signs and the different colors shows their opposite sign, whereas the p orbital can have opposite sign in the form of positive and negative values. Here there are two opposite sign containing wave functions, and the combination of these wave functions will favor the bonding and anti-bonding conditions. Sigma bond formation takes place by the wave function psi1 and psi2. For the sigma bond formation, their combination or addition will give rise to the sigma bonding. The same sign or positive values combine or overlap to give rise to the bonding. The necessary condition for the sigma bond formation is that the orbitals should overlap in a head-to-head fashion. This is a head-to-head bonding overlapping fashion, and this will give rise to the bond formation conditions. The main features of bonding orbitals are they occupy the electrons in between the nuclei of the atomic orbitals. The high density between these two nuclei will give the stability to the molecule, and they possess the lower energy than that of atomic orbitals from which they are formed. Now come to the sigma anti-bonding formation. In this type of bonding, the psi1 and psi2, the two functions, get subtracted with each other. Their values got subtracted and we get the resultant wave function for the anti-bonding formation. The opposite sign or positive or negative values containing orbitals combine or overlap to give rise to the anti-bonding orbitals. The antinode formation in between these two orbitals takes place, which is a electron deficient place. Some features of this type of anti-bonding orbitals are they possess higher energy than that of atomic orbitals from which they form. Probability of finding an electron in between the nuclei is negligible, and electron density is concentrated at one nuclei at a particular time. For the pi bonding formation, the molecular orbitals should overlap with a lateral fashion. This is a lateral fashion of overlapping in case of pi bonding formation. The molecular orbitals does not lie directly on the internuclear axis, and they can remain in between the axes, and this is the pi bond formation for the p orbitals. The pi bond formation takes place the lateral overlapping of p orbital lobe of same sign. These two same sign orbitals should remain at the same side for the overlapping to take place. If they are not on the same side, then the anti-bonding formation conditions favors, and this is the lateral overlapping of p orbital lobes of opposite sign. These two signs will favor the pi anti-bonding formation. The molecular orbital diagram involving s and p orbitals are as follows. This shows that 1s orbital, 2s orbital and 2p orbitals of the atoms of carbon will give rise to the different types of atomic orbitals of the molecule. These are the atomic orbitals of atoms, and these are the molecular orbitals of the molecule to be formed. The electrons filling in these atomic orbitals gets filled with the molecular orbitals of different energy levels. This molecular orbital energy diagram with strong S and P interaction will give rise to this type of energy level of molecular orbitals, in which this is 1s, 2s, 2p orbitals, and this will give rise to sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2p x and y, sigma 2pz, pi star 2p, and sigma star 2pz. This type of energy orbitals would favor the homonuclear bonding of molecules. For example, lithium, boron, carbon, nitrogen. And from this molecular bonding, we can also complete the heteronuclear molecules of different atoms. For example, NO, BO, CO, CN. The complete molecular orbital diagram gives first fill in the valence electrons in the atomic orbitals, and then the electrons should be filled in the molecular orbitals formed as a result of sigma and pi bonding. Filling of electrons would take place according to this rule of filling electrons. Sigma 1s contains 2 electrons of maximum multiplicity. Sigma star refers to the anti-bonding condition of s orbital. Sigma 2s results from the atomic orbital combination of head-on-head overlapping, and sigma star anti-bonding condition favors from the opposite lobes of atomic orbitals. These are pi orbitals combination, and these are pi orbital anti-bonding combinations. And the electrons can be filled as in the atomic orbitals filling. Here, this is the energy diagram for the oxygen molecule. The electrons are getting filled with the rules following Ohm's rule and Pauli exclusion principle. And this electronic configuration can also be used to calculate the bond order, bond length, magnetic properties of oxygen molecule and oxygen ion. Dianion of oxygen can also be calculated for this electronic configuration. For heterodiatomic molecular orbital diagram, we follow this electronic configuration of sigma 1s2, sigma anti-bonding 1s2, sigma 2s2, sigma anti-bonding 2s2, pi 2pxy4, sigma 2pz2, pi anti-bonding 2pxy, and sigma 2pz anti-bonding. Rest of the diatomic heteromolecules will also follow the same molecular orbital diagram. For this, we can calculate the bond order also. Bond order is equal to the half of the difference between the number of electrons in bonding and in anti-bonding. That is half Mb minus Na. What is Mb? Mb is the number of electrons in bonding orbitals, whereas Na is equal to the number of electrons in anti-bonding orbitals. The bond order, if it is greater than 0, then molecule is a stable molecule. If the bond order is less than 0, then molecule is unstable. So from this bond order calculation, we can calculate the stability of molecule. The bond energy of molecule can also be calculated from this bond order. The greater is the bond order, the greater is bond energy. So the bond energy is directly proportional to the bond order. As the bond order increases, the energy will go on increasing. Bond length is inversely proportional to the bond order. As the bond order goes on decreasing, the bond length goes on increasing. It means the greater is the bond length, the lesser will be the bond order. The electrons are paired in bonding and anti-bonding, then molecule is a diamagnetic molecule. Whereas the molecular orbitals containing unpaired electrons in bonding orbitals, then molecule is paramagnetic. So the molecular orbital theory provides us the opportunity to calculate their magnetic behavior. And what is bond energy? The bond energy is the average energy required to break a bond in a molecule of the substance. There are different types of bond energies available in our list. The CH bond will give 413 kilojoule per mole and CC bond is 348 kilojoule per mole. There are certain factors which affect the bond energy. And what are those factors? The first one is electronegativity. The higher the electronegativity, higher is the bond energy. It means the electronegative atom will attract the shared pair of electrons towards itself, and the bond will be smaller, and higher energy should be applied for breaking this bond. So the higher the electronegativity, the higher is the bond energy. Next point is atomic size. What is the effect of atomic size on the bond energy? If suppose atom is a smaller of size, then the higher is the bond strength and higher should be the bond energy to break its bond. The hybridization will play its role in the bond energy. The greater is the S character, the higher is the bond energy. It means the S character, greater the S character will include the electron into itself, and nearer to the nucleus the S character occupation for the electron gives the higher bond energy. For the higher bond order, the higher the bond energy. The number of bonds increasing, the required energy to break the bond should be of higher caliber. So these are the factors which affect the bond energy according to their level. We have studied two theories, the valence bond theory and the molecular orbital theory. And what are the difference between these two theories? Now we will discuss about these two theories in a comparison chart. Here is the comparison chart. What is the valence bond theory? The electrons in this, according to this theory, in a molecule are localized as if they are in isolated atoms, and their identity remains as such. Where in case of molecular orbital theory, a nuclei of the molecule is treated as polycentric and then constructs molecular orbital, and the electrons will remain a part of whole other molecule, and in between the two centers or two nuclei of the molecule. Only valence orbitals participates in the bonding, whereas in molecular orbital theory all orbitals mix to give new molecular orbitals, which further give rise to the filling of electrons in the newly filled molecular orbitals. It could not explain the paramagnetism of O2. According to VBT, we don't know why the oxygen molecule is paramagnetic in nature. Why? The molecular orbital theory satisfactorily explains the paramagnetic character of oxygen molecule. In the valence bond theory, resonance is an integral part. Several structures in this theory are satisfactorily explained their stability order, whereas there is no role of resonance in molecular orbital theory. Besides this comparison chart, there are certain bonds which we have to discuss. For example, coordinate bond. What is a coordinate bond? A coordinate bond forms sharing a pair of electrons which is contributed by only one of the combining atoms. Means in a coordinate bond, the one electron pair is given by one atom only or one molecule only to the another atom or molecule. Through this we can see that positive charge occurs because only the hydrogen nucleus has moved to the nitrogen. Here this bond pair gets shifted to this HCl, and as a result of that the positive charge produced on the NH3 molecule. The negative charge because the hydrogen has left its electron behind. Here the nitrogen gives its electron to the chlorine, so the negative charge obtained as a result of transfer of electron pair to the chlorine. This type of bonding is called coordinate bonding. This is a medium type of bonding. The strength of coordinate bonding is less than that of covalent and ionic, but it is stronger than that of hydrogen bond and other weak interactions. The next type of bonding is metallic bonding. What is metallic bonding and how does it occur? The high electropositive nature of the metals with loosely attached electrons means there is a sea of positive ions of metals, and in between the positive ions, electrons are carrying over. These electrons are delocalized over a metallic crystal. This metallic crystal contains a sea of electrons in which electrons are moving from one place to another place. Sharing of variable number of electrons with variable number of metal atoms. Here the metal atoms can contain more than one atom, and these electrons are loosely bounded to one certain atom. Three theories are proposed in the case of metallic bonding. First, the electron sea model, which is proposed by Drude and Lawrence. The metal regarded as a rearrangement of positive ions called kernel. This is a kernel formed from the electron releasing, which is immersed in a sea of electrons. This kernel is immersed in a sea of electrons in its outermost shell. This shell is not connected with the atoms, but it is a part of this electron sea. Valence bond theory is the another theory which is proposed by Pauling, and it is based upon the resonance theory. Here the resonance takes place between the different atoms of metal bonded lattice. Here the two lithium atoms are connected with each other, whereas the bonding gets shifted with the different types of lithiums, and the charge containing lithium are in between the bonded atoms. The third type of theory is band theory, which is based upon the molecular orbital theory. The next type of bonding we are going to discuss is the weak interaction and in the form of hydrogen bonding. What is hydrogen bonding? It is an attractive force that binds hydrogen atom of one molecule with electronegative atom of same or another molecule of the same substance. For example, this is water molecule, this is oxygen, and these two are hydrogen. What hydrogen bonding says is the binding of hydrogen atom of one molecule with electronegative of same or another molecule. This is the next water molecule, and its hydrogen it get binded with the oxygen of another molecule, means electronegative atom of same or another molecule. In this case it is of another molecule. It is a electrostatic bonding. It is not a permanent bonding. So the hydrogen bonding may be of two types. One is intermolecular hydrogen bonding and second is intramolecular hydrogen bonding. What is intermolecular hydrogen bonding? The intermolecular hydrogen bonding is the bonding between the two different atoms. The hydrogen of one atom gets attracted with the most electronegative atom of another molecule. This is intramolecular hydrogen bonding. Means the bonding between two different molecules with the interaction of hydrogen of one molecule and electronegative atom of another molecule. The next type of bonding is intramolecular hydrogen bonding. Intramolecular hydrogen bonding means the bonding between the hydrogen and electronegative atom of same molecule. Means this type of bonding takes place within one molecule. Here it is orthonitrophenol. It contains OH at one side and NO at another side. Here the oxygen of O, NO2 group, it gets attracted with the hydrogen of OH residing at another place. So this type of bonding takes place within one molecule. This is called intramolecular hydrogen bonding. It is the same case as of orthonitrophenol. Here the orthonitrophenol gives rise to intermolecular hydrogen bonding and orthonitrophenol gives rise to intramolecular hydrogen bonding. This paranitrophenol will interact with the another molecule of water or paranitrophenol. So this is an excellent example of intramolecular and intermolecular. Orthonitrophenol will give a intramolecular hydrogen bonding while paranitrophenol gives a intermolecular hydrogen bonding. There are certain types of bondings also available to different types of atoms. The one is singlet bond and another is odd electron bond. First, we will discuss about the singlet bond. What is a singlet bond? The octet is maintained in singlet bond by means of sharing of electrons. Here, the example of PCl5. In PCl5, the 3 chlorides will bind with the phosphorus with 2 electron system, while the 2 chloride ions bind with the phosphorus with single electron system. So in this system, single electron of chlorine takes part in bonding with the phosphorus. This type of bonding is called a singlet bonding. The second type of bonding is odd electron bonding. What is an odd electron bonding? In which the odd number of electrons takes part in the bond formation. Means odd number of electrons are involved in bond formation. For example, hydrogen ion, in which one hydrogen gets interacted with another hydrogen with the formation of hydrogen molecule, and one of its electron, either this electron pair and this, from these 2 electrons of electron pair, one electron gets removed and this bond will remain as such and give rise to a positive H2 positive molecule. So this is a odd electron bond. These are the main facts for the chemical bonding that I have told you. Thank you very much.